Okay, students, now we will see the second normal form, right? So input is there, and then one NF is there. This is like a filter, right? And then if this filter is passed, or this exam is passed, or this test of one normal form is passed, then you can go for the second normal form. Second normal form. And what is a second normal form? Second normal form says that it's again a kiss text that you see here on this screen. Second normal form says that it has to ensure and it has to satisfy 2NF by removing partial dependencies. Okay, partial dependencies. So here the key word in second normal form is what? A partial dependency. We will, write it in a simple form or in a shorthand form as partial PD, partial dependency. Okay, so the main problem in second normal form, or the main problem that we are dealing in second normal form, is what? A partial dependency. So two requirements are there. The table should already satisfy one NF. Haphazardly you cannot come, or randomly you cannot come in a second normal form. You have to come via first normal form only. So the table should already satisfy the one normal form, and then remove attributes that depends only on the part of composite key rather than the entire key. That means removal of partial dependency. I told you that this is a bookish text, so you have to understand a little bit. What is a composite key? Now you know that any candidate key having two or more attributes, then this candidate key is called composite key. Okay, it will be a candidate key only, but it will be specialized, a candidate key. So it is saying that only on the part of a composite key. So in this, a second normal form, we are dealing with some kind of a composite keys also. And the effect, you can say the outcome after applying the second normal form is, uh, after you apply the second NF, non-prime attributes will depend only on the entire primary key. Okay, it is difficult at this point. So let's slowly try to understand this second normal form. Okay, so I have put it in a very simple way. The first point, just rewritten these things. The first point, relation should be in 1NF, absolutely no problem in this first point. Then the second point, we have minimized it to the least level. And the second point says that there should be no partial dependency. There should be no partial dependency. So now our task, student, is to understand what is a partial dependency. What is a partial dependency, right? So partial dependency says that part of a candidate key determines non-prime attributes, non-prime attributes. So again, if you try to understand one term, another term will come. So here a term, which term is coming? Non-prime attributes, non-prime attributes. So we need to understand again two more things, and that way we will understand the complete thing. Believe me or not, this is one last two new terms I'm just introducing: prime as well as non-prime, prime attributes as well as non-prime attributes. So here the simple definition for the prime attribute, it says that all the attributes of candidate key. So you can write it, all the attributes of candidate key, right? CK is a candidate key, and non-prime attributes is the rest of the attributes which are not part of a candidate key, rest of the attributes, right? So we have slightly understood the prime attributes and we have understood the non-prime attributes. Now this partial dependencies definition, it is saying that part of a candidate key is determining non-prime attribute. Let me give you an example, very simple example. Let's say we have a relation AB is determining what? C, and B is determining C. So two functional dependencies are there, and we have a relation. This relation is A, B, and C, right? A, B, and C. So if uh, you are trying to compute a candidate key, so remember from the last lecture what trick we can apply. We have to go on this left hand side only just to discover the candidate key. Okay, it's an approach, it's a systematic approach only. So if you go for AB plus, so this AB plus is giving you A, B, and because of this B is determining C, it is giving C also. Now if you go for B plus, so it is just giving you B and C. A is missing in that. So this is a candidate key and this is not a candidate key. Only two possibilities were there, and you can try for all the other combinations. You will find the same results. So here, candidate key is what? A, B. So what is a prime attribute in this case? The prime attributes will become what? All the attributes of a candidate key. So A and B are the prime attributes. Prime attributes. Then what about the other attributes? That means the non-prime attributes. So non-prime attributes is what? Non-prime attributes is C only. This is prime and this is what? Non-prime attribute. Now part of a candidate key determines non-prime attribute. So here if you see B is determining C. All of you please pay attention here. B is determining C. There is a partial dependency. How it is a partial dependency? Because B is a part of candidate key. It's partial. It is partly defined. It is defined in a parts. So it is a partial. And it is also determining what? A non-prime attribute. So this attribute, we have seen that it is non-prime attribute and it is functionally dependent on part of candidate key. So this is what? A partial dependency. So this creates a lot of problem, students, and one of the problem that we can analyze here, right? So in this table or in this relation state, this is a relation state because it has a data also at this point. So consider there is a relation having three attributes R, S, and T. And the values are like this: R, A, T1, S, A, T1, R, B, T2, then S, B, T2, and then again R, S, C, C, T3, T3, and D, T4, and D, T4. So if you try to compute the functional dependencies from this relation, and we have done one exercise also, so all of you can compute this. I'm just writing the final answer, not writing the final answer. I'll give you explanation also. Here, if you see, so RA is determining T1. For any value of RA, there is T1. Okay, so this functional dependency RS is determining T is valid in this table. So you check at any point. RC is determining T3. So whenever you will see this value RC, it will always give the value of what? T3. Always it will give you the value of T3. And then there is one more thing also in this relation state. This relation state, A is determining T1. So whenever A is coming, T1 will come, right? So this you have to see. Whenever A will come, T1 will come. And whenever B will come, T2 will come. So here you see two values are repeating. And whenever C will come, T3 will come. It's just like, a roll number is determining what? A name. So whenever roll number 101 is there, at any point of time, the name would be what? A Rahul only. So you see that A is a T1. Again, A is coming, but T1 is coming. So absolutely, you can write like this: S is determining T. S is determining T. Now, in this table, this is already in 1NF. How come it is in 1NF? Because there are no multi-valued attributes and there are no composite attributes. So this table is, or this relation is already in 1NF. But can somebody think of, is there any problem with this table? Yes, there is a problem with this table. And the problem is, all of you can see that data duplication. Why these two values are repeated? Okay, why these two values are repeated in this? Why these two values are repeated in this? And why these two values are repeated in this? Why these two values are repeated in this? So there is a data redundancy and there is a data duplication. This is a very small snapshot. Imagine you have a large table in your database. So how much problem it is going to cause in this? So this S determines T is basically what? A partial dependency. partial dependency. How can you solve this problem? How can you solve this problem? First, you need to understand, and first mathematically you have to prove that this is literally a partial dependency. So in this, I'm just the first step for the second normal form is to compute a candidate key. So here again, this is the left hand side and this is again a left hand side. So first I will compute the closure set of rs plus, and then I'll compute the closure set of what s. So what is r s plus? Obviously it will give r and it will give s, though no problem in this. Now because of s, it will give, because of s determining t, this partial dependent, this dependency, it will give t also here. It will give t also. So this is forming a candidate key. It is a candidate key. Then what about s plus? You can have s and you can have t, but you cannot determine r. So you have to stop here, and this is not a candidate key. So if you want, then you can go for further and you can investigate r, and you can investigate rs also. Rs is already you have tested, then you can investigate for rt also, and then you can investigate for st also, right? One candidate key you will find is rst only, but that would be the super key. So we are not interested in the super keys, right? We are only interested in the candidate keys. So this we are not considering here, right? Then after that, if you are trying to compute the prime attributes. So remember from just the last slide, what is a prime attributes? Part of a candidate key, or all the attributes of the candidate key, all the attributes of the candidate key. So don't take these attributes, they are the complete attributes. Always go for this. So prime attributes are only rs. Now rest of the attributes, which is non-prime. So non-prime attributes, how many are left? Only one is left, and that is t. Okay, that is t. So non-prime attribute is what? T in this case. So just if we test these two functional dependencies, rs is determining t and s is determining t, is there any partial dependency in this figure? Yeah, obviously we have found out there is a partial dependency. Now we are proving mathematically also. So here if you come, s is what? S is what? A part of candidate key. Part of all of you can see that S is what? Part of candidate key. This is partial, and this is determining what? Non-prime attribute. So if it is determining non-prime attribute, obviously it will become what? A partial dependency. And in this diagram also, you can see that this S is determining T is creating a problem, because it is giving a lot of duplicated data. Whenever you see S is determining C, because the values are repeated, so much wastage of the database space. So this is creating a problem. So we have to remove this partial dependency. And how can we remove this partial dependency? The answer is, we have already learned, the answer is, and the solution is what? Decomposition. Decomposition, right? Decomposition. So what is a decomposition? Breaking a relation into a smaller relation. You can go back to the previous lecture also. What is a decomposition? Decomposition is breaking a relation into a smaller relation. Now I would write it once again. R is a relation and having the attributes R, S, T. So this is just, I have formed it into a mathematical form. No problem with that. And what is a functional dependency that we are taking here? The functional dependencies is RS is determining T, and S is also determining T. S is also determining T. So where is the problem? Which functional dependency is creating a problem? This functional dependency is creating a problem S. Now please pay attention. We'll go slowly and I'll try to introduce the steps. Okay, algorithmic step how you can decompose a data. So whatever the functional dependency is creating a problem, you have to take a closure set of that thing. So here this thing is creating a problem S. So you would take closure of S. Okay, and closure of S would be what? S plus. So what you will determine, obviously you would determine S and you will also determine T, because S is determining T. Now from the main relation, you have to remove those attributes. So you have removed T and you have removed S, right? You have removed T and you have removed S. So now this relation, let me write it once again so that everybody understand this, what I'm trying to say. The problem here is S plus is no S is determining T. So you have found out the closure set of S. So it is giving S and T, right? So you have to remove this T and you have to remove this and you have to put it in a second relation. So you have put it S and T, S and T. This is the first breaking. How many are left? Only one is left, which is what? R. But there should be some common attribute, and the common attribute must be the candidate key. This is the requirement that we have understood for lossless decomposition. Lossless decomposition. So R, you can put it R here, and then you can put it what is the common attribute here, which is the candidate key. So S, you can take it. Okay, so the breaking, final breaking is what? Relation into relation 1 and into relation 2. Here you can write the functional dependency S is determining T. S is determining T. Now, if you try to decompose this actual table, how the table will look like, because you said that relation 1 is RS and relation 2 is what? ST. So let's break this down table also. Let's break this down table also. Now, let's break this down table, and here is the table RS. So here RA, SA, RB, SB, RC, SC, RD, and SD. So all of the combinations or all of the tuples are unique. There is no a repetition in this. But from this we have actually removed, or we have actually saved a space of at least 4 tuples. So A1 is determining T. This is we have taken. Now this repetition we have not taken. Next thing we have taken this repetition we have not taken. Next thing we have taken this, and this repetition we have not taken. Similarly, this thing we have taken, and this repetition we have not taken. So S and T is the second table. S and T is the second table. So this is the final decomposition, and here clearly you can see absolutely in this table there is no problem of data duplication. Can we recover the original relation from the client that we have received? Yes, we can recover, and we can recover with this natural join, with this natural join. So if you take a natural join of these two relation, you will get the same table. This is damn sure, and it should be the case. Otherwise the decomposition will not be a lossless, it will become a lossy decomposition, and you will have some spurious tuples and you will miss some of the important tuples also. So let's just see RA into AT1. So A is matching, so first row will come what? RAT1, and you can see that RAT1 is coming. Then B is not matching, C is not matching, D is not matching. SA, so SAAA is matching, so you can go like this, SA, and then T1. Here T1 is there, so second row is also coming. Likewise, you can reconstruct the original table also. So this is the beauty of what? A decomposition. So this was the given relation RST having some problems, and then you have decomposed into 2 parts. Now all the problems are solved, at least at this point, and this decomposition is lossless, and this decomposition and these two final relations are in 2NF. They are in 2NF. Okay, students.